Okay. Okay.
All right, yeah, let's get started. Hello, everyone.
All right. So I guess I'll just get started. Hi, everyone, and thank you very much for being here. And thanks, Laura and Hans and Faye, and for organizing and having me here. So I'm going to talk about this title here, diamond rings, just because it sounds kind of catchy, but it's really the name of a property that exists, and I'm going to try to explain what it is. My motivation to be looking at this comes a little bit from the non-commutative world. But then while looking at this, I realized that even in the commutative world, not much, I mean, there was something done, but not much towards understanding the generality and what this property means. So I'm just going to start with the definition. So that's the definition. So I'm taking R to be a ring. Um, and I'm going to say that this ring R has the diamond property. So I'm not going to call it diamond ring because it would be just too much to do that all throughout this talk. It has the diamond property if for all simple R modules, let's say we're talking about left modules now, every finitely generated submodule M of the injective Hall of the simple module S, so E of S is the injective Hall of S, is Artinian. Okay, so what we do is the following. You look at simple modules, you look at the injective Hall of the simple module, and we want to make sure that finitely generated submodules of this injective Hall are Artinian. Okay, so that's the condition. And that's called the diamond property. I'm going to try to justify a little bit why it's called like that, but what I'm going to say is justify why I think it's called this, because I don't know for sure why it's called like this, but probably can be something else. Just a note first. So suppose you have a left Noetherian ring. If you have a left Noetherian ring, then this is actually equivalent to asking that any such module has finite length. Because so suppose that the ring is Noetherian, then if you take a finitely generated submodule of V of S, right? So this finitely generated submodule M here, well, the ring being Noetherian, that means M is Noetherian itself, but I'm also asking that the module M is Artinian. So if I'm asking that the module is both Noetherian and Artinian, then it means that I'm asking it to be of finite length. So if you think about it, what it means that the injective Hall is what we call locally finite. So that means if I'm saying every finitely generated M has finite length, it means that the injective Hall, in fact, is a directed union of modules of finite length, right? So of course, every element in the module belongs to some submodule, and then that's finitely generated or cyclic even, and that means that the injective Hall is what we call locally finite. So we say a module is locally finite if it's the sum of its submodules of finite length. And such modules, I'm going to come back to this a little bit later. Such modules are very important when you do representation theory and you want to look at categories of finite dimensional modules. But let me first, before moving on, let me first note that if R is a commutative Noetherian ring, if it's a commutative Noetherian ring, then R does actually have this property, and that's actually been proved. It's a result of MATLIS, and it's it's not necessarily right now. I mean, in modern days, it's something that you would think of not something very difficult to prove. And here's my picture of this injective Hall, and this is my explanation of why I think this is called the diamond property. So the explanation is the following. So suppose you have even let's suppose we take a commutative ring, which I'll be doing more and more. From some point on, all the rings will be commutative. This is, after all, the commutative algebra seminar. So when R is a commutative ring, I noted that this is a local condition, but let's say we have even a commutative local ring. Um, if I'm asking something about finitely generated modules, I can just look at cyclic modules. And when, say, for example, when you have a local ring, that means that we are actually going to be looking at some submodule M of the injective Hall, which is colored in green here on this picture. So this picture here is the injective Hall. It has a simple socle, so it kind of has only, imagine it as a lattice of submodules, right? So something at the bottom, it has just a simple socle at the bottom. This green module is the cyclic module, which is in fact also local. So a module is local if it has a unique maximal submodule, which contains all the other submodules. So you see that it kind of looks like a diamond. This submodule M that I'm talking about here has to be a submodule of the injective Hall. So it has a simple socle, but just one piece at the bottom, and it has only one piece at the top. So this is the top and the bottom. So that means it's just kind of emanates and comes back into this top. Modules like this, which have a simple top and a simple bottom, are usually called diamond modules in evident representation theory. And you could even give an example that starts exactly from this picture that I have here, from this really this diamond picture. If you take that picture and you interpret it as an oriented graph, so if you put like orientations on the arrows, and you take what's called the path algebra of that quiver. So you just put arrows in all following the same directions. Um, then corresponding to that picture, there is a module which has exactly this property, that it has simple top and simple bottom. So simple top means you have a unique maximal submodule, and simple bottom means you have a unique minimal submodule, and everything in the module is contained between those. So it's kind of like a squeezing in and squeezing out. So this is why I think this is called the diamond property, because really it asks something about these diamond modules. It asks that these diamond modules have finite length. Okay, so again, this is a terminology. A diamond is something that has simple top and simple socle. So let me just go a little bit into the history of this. So as I said before, Mottlis proved that Noetherian implies property diamond. So if you have a Noetherian module ring, then the injective Hall of every simple is what we call locally finite.
Yeah, ask
But
something.
yes, yeah, go ahead, Philip.
So is that on the same side? If it's your diamond is on the left, right? You basically define left diamond.
Right, that's right.
And does the ring have to be left Noetherian for that?
So here's the thing. I'm gonna say something which I think is very interesting. Right now, I'm actually saying let's consider that the ring is commutative.
Oh,
So I'm already saying let's say R is commutative. I'm going to say a little bit about the history about the non-commutative case. But yeah, I should have actually stated this more clearly. So right here, I have a commutative ring. So Mottlis proved that Noetherian implies property diamond for commutative rings. And as Philip was saying, we can define the left property diamond and the right property diamond if we want to for a ring. Okay, so for commutative rings, Noetherian implies property diamond, but even more. In fact, in this case, not only the injective Hall is locally finite, but in fact, this injective Hall is Artinian as a module. So it's not just locally finite, or like locally Artinian, if you'd like, but it's actually Artinian per se. And then Vamos studied rings which have this property. What property? The green, the property highlighted in green here. So the property so let's say a ring is commutative. When does it have the property that the injective Hall of every simple is Artinian? When does it have that property? Vamos studied these rings, and he called the rings with this property co-Noetherian. because in a sense they have a dual property then being Noetherian. It's like you don't look at the ring itself, or maybe projective finitely generated modules, but you look at the dual things, the injective modules and you want those to be Artinian. So he called those co-Noetherian. And then using work of Matlis, Jans proved that in fact a commutative ring is co-Noetherian if and only if it is locally Noetherian. So a commutative ring, again, everything is commutative, is co-Noetherian if and only if it is locally Noetherian, in the sense that the localization at every maximal ideal is Noetherian. That's kind of kind of interesting. At least at first, when you learn about Noetherian rings and commutative Noetherian rings, you wonder what are these properties local or not, um, and this this kind of gives exactly what this means. Local Noetherian means that the injective hulls are Artinian. Um, so the actually the above shows that now if we have this, we can also see that locally Noetherian, meaning co-Noetherian rings, do have property diamond, because if their injective hulls are Artinian, then of course they are locally finite. Um, so using this property of Jans, actually that extended a little bit the work of Matlis, and showed that these rings also have this property diamond. Uh, so that's kind of the a little bit about connected history to the property diamond for the commutative case. I'm going to say a few things about the non-commutative case. So starting here, I'm going to say a few things about that. And the interest perhaps in the property diamond has been a bit more from the non-commutative world than it's been from the commutative world, especially because it somehow implicitly appears in work or attempted, when you attempt to resolve this pretty well-known conjecture, which is called Jacobson conjecture. So what is this conjecture? This conjectures that if you have a ring which is two-sided Noetherian, so if you have a two-sided Noetherian ring, obviously non-commutative, then the intersections of the powers of the Jacobson radical is zero. Okay, where this J is the Jacobson radical. So that's a conjecture, and there's work that's Jadagankar has proved this for certain classes of ring, which are called fully bounded Noetherian rings. I'm not gonna I don't want to go into details of what that is. So there are certain classes where this goes, but it's not really known in general. But somehow, and we'll see later why, in fact, the property diamond is actually very closely related to intersections of ideals. Um, so let me just continue a little bit with this. So there's been plenty of people who've tried to look at this in the non-commutative world. Ian Musan, one of these people, Roseblade, and as I said, Jadagankar implicitly kind of used similar techniques, and Paula Carvalho, Machuk, and Brown, and others. Um, and just for a first example, here is one such class of rings where this has been looked at, namely group algebras of polycyclic bifinite groups. Now, why am I highlighting this? Um, the group algebras of polycyclic bifinite groups are in fact Noetherian algebras. They're Noetherian rings, two-sided Noetherian rings. And it turns out that these Noetherian non-commutative rings, two-sided Noetherian rings, don't always have this property diamond. So quite strangely, this doesn't necessarily have property diamond. There's certain situations depending on the group, but more technical, where this that controls when this has this property or not. This has also been looked at even quite recently, as maybe a year ago. A paper appeared just a year ago, maybe, for certain Ore extensions. So you take a ring R and you take the ring of polynomials, but you twist that by an automorphism. So that's a standard construction in non-commutative algebra. And Carvalho and Brown and Matschuk looked at when does this have this diamond property, let's say on the left. And it turns out that they found very interesting connections to geometry, and their answers have to do, they looked at the case when R is affine. So you just take a finitely generated commutative algebra and trying to prove when, to see when this R of X and sigma has this diamond property. And it turns out that in many situations is related to whether this ring R of X and this OR extension has the property that all the simple modules are finite dimensional. In the infinite and dimensional, in a non-commutative world, we have of course examples of simple modules that are infinite dimensional. And they also found a lot of connections, even for the case when R is just commutative polynomials in one variable. So just complex numbers adjoin X and Y, for example, and they looked at an automorphism, which is just an affine automorphism coming from a linear transformation on the linear polynomials extended to the ring. Even then, they found very interesting connections to geometry of the affine space of this property. So there's been a lot of work and interest in this situation. So then I thought, okay, I'd like to, my motivation, I'd like to understand some of these connections to, let's say, this Jacobson conjecture, but also other properties in the non-commutative world, especially questions like what types of algebras have this properties like all modules, all simple modules being finite dimensional. One such class of rings is the so-called called polynomial identity rings, which do have this property. But what other classes of rings have those properties? And then there's a lot of interconnection that's happening here. So I wanted to at least say, okay, can I at least understand what happens in the commutative case? So that would be the place to start to completely understand what's going on with commutative rings. So therefore, I'm going to start with from now on with the assumption that R is a commutative ring. And while trying to do this, so what I was always trying to do is to make sure that I can give some proofs, but which are not going to be perhaps which would use methods of commutative algebra, but certain methods that could also have non-commutative analogs. Like localization is fine. There's non-commutative localization, and certain techniques, categorical or homological or topological, that could be perhaps extended to non-commutative rules. So this is what I'm trying to, I'm going to try to at least maybe point out in various places. So here's a first result that's is not very difficult to see, but I think it's a bit illuminating in a sense. So take a commutative ring. Then the ring has property diamond if and only if every ideal of R is an intersection of cofinite ideals. So what is a cofinite ideal? I'm writing this definition here. So for now, for us, an ideal of a ring R, remember the ring is going to be commutative from now on. The ring, an ideal, we call it cofinite, is if the quotient has finite length. So perhaps a little bit not very fortunate terminology. I don't mean that R mod I has to be a finite ring, but I just need R mod I to have finite length. So to be Artinian, an Artinian ring, commutative. And property diamond is so this is not very difficult to see. It's fairly easy to see. And property diamond also is equivalent to, as I said before, the fact that the injective Hall of simples are locally finite. And another reformulations is to say that ideals of R are closed in the so-called full cofinite topology. So the full cofinite topology is the linear topology generated by all cofinite ideals. Okay, so that means you declare all these cofinite ideals to be open. You generate a linear topology by saying, okay, translations, you multiply an ideal or add an element to it, and that's a coset. Those are open sets. And then everything that you can get by, of course, by unions of these are going to be open. So just like a regular algebraic type of topology. So this is called a full cofinite topology. And the proof of this is very, as I said, is very easy. The idea is that every ideal of any ring, even non-commutative rings, but let me just keep everything commutative. Every ideal can be written as an intersection of what I call, for maybe lack of a better word, strongly irreducible ideals. So what is a strongly irreducible ideal? It's an ideal which is not only irreducible in the sense that you cannot write it as an intersection of two larger ideals, but more than that, you ask that the quotient R mod the ideal has simple socle. So that means that you have this ideal Lj, and there is a unique minimal ideal that sits over it, and then everything else is possible on top of that. So a strongly irreducible ideal, and it's not just you cannot obtain it as an intersection of two, but there exists a unique ideal on top of it, and nothing, and then above anything can happen. Any ideal is an intersection of such ideals, not finite, of course. I'm not, that would be too strong. So it could be arbitrary, but the point is that you just whenever you have an x that's not an I, it's the basic observation that if you take an element that's not an I, you can take a maximal L with respect to the containing I, and maximal with respect to the property that it doesn't contain x, and that will give you exactly a strongly irreducible ideal. So yeah, so that's 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 all we need. And then the hypothesis that we have here, if we want this ring to have the diamond property, then any such quotient by a strongly reducible ideal, because it has simple socle, it has to be embedded in the injective hull. But if it's embedded in the injective hull by the diamond property, it has to be Artinian. So therefore, any such quotient has to be finite length. So if you have the diamond property, then you have every ideal is intersection of cofinite ideals, and even conversely, you can see that too. Here's another result, that the diamond is a local property. So this is something that I've only seen in a paper maybe a couple of years ago of one of the authors I mentioned, and two co-authors. Perhaps my favorite way of seeing this is by drawing a diagram like this. And the reason is, again, that I want to be able to have a method that I can find perhaps in the non-commutative world. So I prefer to think about the localization functor in such a way as a tensoring by Rm, and there's an adjoint of this functor, sort of the kind of a forgetful functor from Rm modules to R modules. If you just take the natural map from R to the localization, and this is a kind of a strong type of a junction. Well, a strong type. It's technically it's this functors are called what separable, but nevertheless, the main thing is that this functor f has to preserve injective modules. Whenever you have an adjoint a pair of functors like here L and F, and L is exact like localization, then F has to preserve injective modules. So that means that the injective hull of the simple module in the category here is transported via the functor in here, which essentially means that in order to take the injective hull of a simple module, you only need to take extensions, and you need to sort of complete it essentially with respect to simple modules of the same type, in a sense. So it may be very large and it's not necessarily locally finite, but the point is that you could just look at the injective hull of the simple module in this category and then take it via the functor f, and that will give you the injective hull this category. So it kind of just, that means just sort of forgetting that it's an RM module and thinking of it as an R module. And that's all you need to see that this is a local property. That's because just a simple
sorry, can I ask, the M's here, are they maximal ideals only, right? It's not prime ideals.
That's right. That's right. So whenever I say something is local, I will actually refer to from the point of view of maximal ideals. Yes. Thank you for that's a very good point. Yeah. Yes. Right. So it's local in this sense, if you can. And one of the things that it's since we are here, one of the ways to think in non-commutative in the non-commutative world is to, since in the commutative world maximal ideals are more like points, so you go to the non-commutative world, and then you look at these injective halls of simple modules, and they kind of take over the roles of the simple module. So you look in the category, and then these objects are kind of taking the role of that. So we're going to be interested in looking at this. And here's another example which I found interesting, and also because it was very late when I realized that this is actually true. So if you take a finitely generated K algebra, so let's say a commutative finitely generated K algebra, just a quotient by a polynomial by some ideal, and let's say over an algebraically closed field, then every ideal of A is an intersection. So every ideal of A is an intersection of ideals of finite codimension. So ideals such that A mod I is finite dimensional. So in affine algebras, of course, we know that prime ideals are intersections of maximal ideals. So therefore, maximal ideals, at least over an algebraically closed field, are just all codimension 1. But this, goes farther than just prime ideals. It goes to any ideals. All ideals are such intersections. And kind of, perhaps this is not necessarily a useful thing in commutative algebra, but strangely enough, I saw this only in the book of Sweedler, which is a book on Hopf algebras from the 60s. And I don't know, perhaps there's, he didn't really make reference to, I think, to other book. I don't remember clearly, but I was surprised that I've only seen it in this textbook. Nevertheless, the reason why this is interesting is because, as I said, in the world of representation theory, if you have an algebra and you want to study its finite dimensional representations, sometimes you need to complete that category with respect to inductive limits, because then it's like quasi-coherent sheaves. Once you complete them, you're going to start having enough injective objects. There's going to be a growth in D category, so you can do homological algebra, and you can do all sorts of interesting things. So this is why this is also important there, because if you have an algebra and you can you know that you have enough finite dimensional representations, so that means that ideals are intersections of cofinite ideals, or at least zero is intersection of cofinite ideals, then you have something to work with. Okay, so going back to just the commutative case, gonna just list a couple of results and a couple of things that we can do with the diamond property. So here's this first lemma over here, which says that if R has diamond property, and you take any ideal and a finitely generated module, then the intersections of the powers of I times M is 0. And if you would like to erase this M, you could also say that if M is just R, you could just say that the intersection of the powers of I is 0. And of course, immediately we think about, well, this is Krull's intersection theorem, right? It's kind of Krull's intersections theorem. This, yeah, I think I missed a hypothesis here. I want this to be a local ring. So what this says is that, in fact, Krull's intersection theorem works in the generality of diamond rings. And in order to kind of work and prove some of these things, this other lemma is also useful. So if you take a local Noetherian ring which has simple socle, then it is Artinian. Now, this is something that's known. It's not new. However, you can, if you carefully do the proofs in the sort of a correct order, then you're going to end up with being able to prove lemmas like this one over here, without using some of the things that's being used usually. Like, for example, for Noetherian rings, sometimes the proof is using the Artin-Rees property, or so I wanted to be able to do it in a non-Noetherian case if the ring has just the diamond property. And then this turns out to be somewhat useful. So I actually wrote the one possible proof here that again, the reason I did this, and some of the things I'm trying to do is to be able to write some things in a way that would carry over to non-commutative to the non-commutative world. So for example, this lemma here, I want to prove that no, I want to prove this lemma that if you have a local Noetherian ring with simple socle, then it's Artinian. So how would you do something like this? Again, this is something that's not new, but to just give you an example of something that you could try to phrase in a way that's perhaps applicable to the non-commutative world. You take you can reduce this to the maximal. You assume that we are working with the maximal ideal, so I'm having a local ring here. And you just take an element in the maximal ring and you take the left multiplication. You take the sequence of kernels, so annihilators of powers, but I'm just thinking of them as kernels, and as usual in fittings lemma, you're gonna need to be stationary at some point because this is Noetherian. So whenever the kernel of phi to the n is equal to the kernel of phi to the 2n, then as in fittings lemma, what you have is that the image of phi to the n and the kernel of phi to the n have to intersect to 0. So that's just a standard module theoretic thing to prove. But the other thing is, now you notice that the kernel of phi to the m is actually not equal to 0. And the reason is because you have simple socle, this simple socle, and if you have simple socle, that's a simple module, it has to be annihilated by m. If it's annihilated by m, it has to be annihilated by this element that we started off with. So therefore, it has to be in the kernel of any power of this map phi. But what that means, well, this socle is also essential here. That means that the intersection of two non-zero things cannot be 0. So if the second thing is 0, the only thing that we get is that, in fact, the first thing has to be 0. Oh, sorry about that. So what we get is, in fact, is that phi to the n is the 0 map, or a to the n is 0. So you get that m is nil, and therefore nilpotence in this ring is Noetherian. And this is something that works also in the non-commutative ring world. So there's several things that can be carried over to the non-commutative world. So that's the only reason I wanted to sort of outline a little proof here. So anyway, just moving on. So we do have a Kroll intersection theorem for this for modules with diamond property, and the way you would go about treating that is, you, as always, when you have a property for a ring, it's useful to actually look at modules and say, does it have any meaning to have properties with that module? So, and it turns out to be useful as usual. So you would say that M has the diamond property if every submodule is an intersection of cofinite submodules. So you just declare this to be the diamond property for a module. And then, of course, the first thing you would say, what are the properties of this thing? Closure under submodules, quotients, direct sums, extensions. And it's easy to see that it's closed under submodules and quotients. It doesn't seem to be easy to note whether this is closed under direct sums. So I think this is something that I thought about it a little bit, and I couldn't figure out if this is closed under direct sums. It's not closed under extensions, but it's not clear if it's not closed under direct sums, at least to me. So, but that's that's not something that we need. So this says that finitely generated modules, also finitely generated modules over a ring, actually, a ring with property diamond also have property diamonds as modules. And the idea is pretty simple. Again, the same the same story where you take a module and you can write every submodule as an intersection of submodules which are strongly irreducible, like before. So these are modules, such submodules of M, such that these quotients have a simple socle. So these are strongly irreducible, and whenever now if I have the diamond property and I know M is finitely generated, then if these are finitely generated and have simple socle, then as before they have to have finite length because R has diamond. So that just means that every submodule is an intersection of submodules with of cofinite submodules. So again, it's the same idea that why this is actually related to the property diamond of modules. And now once you've got this, you can prove this cruel intersection theorem. Remember, this said that if you have a local ring with the diamond property and a finitely generated module, then the intersection of the powers I to the n times m is 0. And it's quite immediate. You just assume that the ideal is maximal. You can just take the maximal ideal without loss of generality. And as before, we noticed that M has the property diamond. So if you take any element of this, you can avoid it by some cofinite, as we notice here. We can avoid it by some cofinite submodule of M. But then if that's cofinite, then this means that this has finite length. And if it's finite length, it's going to be annihilated by a power of the maximal ideal, which is I here. For some n, which could prove just immediately directly. I mean, but it's classically known. The reason I'm mentioning this is because I'm trying to say I'm not using anything from Noetherian commutative algebra. And so therefore, that means simply that I to the n is contained in M, and x is not contained in I to the m, so x is avoided by some power of I to the n m. So in other words, this this proves the cruel intersection theorem for rings with this diamond property. And another note that I wanted to make here, just going back to the Jacobson conjecture, Jacobson conjecture is in fact a form of a cruel, some form of cruel intersection theorem, right? So that's what the Jacobson conjecture says. You take the Jacobson radical of a ring, you take all the powers of the Jacobson radical, and that's supposed to be 0 if the ring is both left and right Noetherian. So this is very, very closely related to this diamond property and to methods that seem to show up in trying to assess what properties these rings have. Okay, so as always in any situation, you want to perhaps know at least is there some characterization for the local case? What is the can you characterize when is a local ring? When does a local ring have the diamond property? And so here are the equivalent statements. If you take a local commutative ring with maximal ideal M, then the fact that R is Noetherian, as we have seen, well, kind of, but in this case is equivalent to the fact that the injective Hall of the simple module R mod M is Artinian, and is equivalent to R having the diamond property and the fact that the quotient is finite dimensional over R mod M. So in other words, finitely generated. So this tells us what is the difference between the diamond property and the ring being Noetherian. And just to make sure that we have the terminology right, I meant to say this before, sorry about not saying that. When I say local for a ring, I mean it has a unique maximal ideal, and that's all I mean. And I'm saying this because oftentimes in commutative algebra, when you say local ring, you might mean local Noetherian. So local is just local, but not Noetherian. So this kind of says that it's the diamond property. It's not too far in a sense from the Noetherian property, or at least in terms of property of tools that still work. As we've seen, the cruel intersection theorem, kind of surprisingly, at least for me, worked in this generality, and for local rings, the difference is just in m mod m squared being finite dimensional. So that actually,
A quick question. Yeah, I think you said it, but I just want to double check that that's what you said. The condition m mod m squared is finite is really just saying that m is finitely generated, right?
Yeah.
Nakayama's lemma, right? Okay.
But see, we have to be a little careful. Nakayama's lemma, we usually use it for Noetherian rings, right?
I know, that's why I wanted to make sure that the condition m finitely generated is equivalent in this case.
So if you just take an arbitrary local ring,
I think it's still true, no?
Yeah, I think it's true. I think it's true. I think Nakayama's lemma holds as long as you're working with a finitely generated module, regardless of whether the ring is Noetherian.
Yeah, right.
So the equivalent should hold.
Yeah, it holds here. It holds here. Yeah, there are. I mean, if the ring is not local, there may be problems. But here it does. Yes. Yeah, I believe you're right. Yes. So this is essentially what it's saying. So here's another closely related result. I thought, okay, so how about the cruel intersection theorem? Is there some relation to, when does the cruel intersection theorem work? So perhaps kind of interesting to note is that if you take again a local ring, a local commutative ring, we're not assuming it's Noetherian, then R has the cruel. It's a cruel intersection, so that means what I mean is that every quotient of R satisfies the cruel intersection theorem, which is the same to make the statement that for all ideals R, this intersection is equal to L. So all quotients satisfy the cruel intersection theorem.
So that would also then be the same as saying that every ideal is closed in the emetic topology, if you want to say it in topological sense.
That's right. That's right. Well, I'm going to get to that. Yeah, I'm going to get to that.
Okay. Sorry.
It says that every ideal is closed, but we're if you take the quotients, that's right. I think that's right, because we're taking this I is it just says that every ideal is intersection of the maximal ideals plus L. Right. Yes, I think that's equivalent to saying that. Right. Yes. Yeah, and you're actually right. I even actually have this in the paper. So yeah. Yes. And so it's equivalent to actually asking that the injective Hall of the simple module is locally finite of Lowy length less or equal to omega. So yeah, that's another kind of nice connection to the Lowy length, to the properties of the injective Hall. So anyway, these things here allow us to get various types of examples. So any von Neumann regular ring commutative, just commutative here, is an example of having this property. Every local ring for which m squared is equal to 0. So that's maybe kind of not that interesting, but I'm trying to give examples of non-Noetherian rings. Then if you take a local ring for which a power of the maximal is 0, and also if you mod out by the socle, you get an Artinian ring. So you're kind of asking that the ring has a large socle. So that's not too far, perhaps, from the case of an Artinian ring. And then there are examples that you can obtain by various types of Ries constructions, Ries ring construction, or the associated graded ring construction. If you start out with certain rings that have a it's a more technically expressed rational property. But perhaps it would be interesting to note that this example 5 here, that you can have a local ring for um, which the Jacobson is nilpotent, the maximal ideal is nilpotent, um, and every so every quotient, so the R mod Sokal has the diamond property. So that means, in other words, every ideal which is non-zero is an intersection of cofinite ideals. So every quotient has the diamond property except for the quotient by the trivial, by the zero ideal. So R doesn't have the diamond property, but every proper quotient has the diamond property. So this is kind of very, very sensitive to constructions, and this is the example here that I highlighted in blue. So the thing is that you have this simple Sokal again, and then if you mod out by m cubed, you have you can show that this has the diamond property. Nevertheless, showing that something has this diamond property is not necessarily an easy thing to do outside of the Noetherian world, which kind of says, all of what I'm doing so far, I think, at least from the point of view of the properties, shows that this class of rings is not too far from Noetherian rings. They have cruel intersection. When the local ring is just that m mod m square, so that's just that's the difference. So what to me was surprising was this last thing, and now I'm going to go to topology. So looking at complete rings. So as we have seen so far, a natural type of topology appears here. So I'm going to call a topology a cofinite topology. Again, a commutative ring. It's just a linear topology which has a basis of neighborhoods of 0 consisting of cofinite ideals. And we call this the full cofinite topology in case we're talking about all cofinite ideals. So if you take all the cofinite ideals, that's the full. If only some are open, then you call it a cofinite topology. And just classical examples, if you take the ring just polynomials with if you declare x to the n open, then of course not all ideals are going to be open. Like for example, all ideals generated by a polynomial which is not divisible by x, they're not going to be open ideals. So there could be ideals that are not open, and k of x with the usual topology. Of course, powers of x is in fact also topology that's generated by cofinite ideals, and this is actually the full cofinite topology here. And it's very easy observation to see that if you consider a complete local Noetherian ring, so by this I just mean the usual thing where this is complete with respect to the m-adic topology, its topology is actually generated by powers of m, but powers of m are cofinite here, quite easy to see. So this is actually a cofinite topology. But again, it's not difficult to see that this is the full cofinite topology. The same argument I did before. If you take a cofinite ideal, there's going to be a power of the maximal ideal that annihilates R mod I. So if you take a cofinite ideal, that means there's some power of m that's going to be contained in I. So I is going to be open in this full cofinite topology. So what this means is that, in fact, if you look at a complete Noetherian ring, the local Noetherian ring, the usual m-adic topology is exactly the same as the full cofinite topology. So no difference. So this cofinite topology does actually show up in many examples that we see, and also this k of x here. So it's a natural thing to use to perhaps replace it in case you don't have a local ring or something that's a little bit more general. So here's a definition. I want to define what does it mean for something to be complete with respect to this topology. And I could just call this complete, and we could just call it this, but it actually has a name. A commutative ring that is going to be called pseudo-compact if it's complete and separated with respect to a cofinite topology. And if you think about it, this is nothing else but saying I'm going to take a ring that's a profinite ring, a profinite limit of Artinian commutative rings. Any profinite limit of Artinian commutative rings is going to be a ring of this sort. And this appeared, I think, perhaps first in Gabriel's work, but perhaps, maybe I'm wrong, and there've been, I mean, the terminology of pseudo-compact. Otherwise, these kind of rings have been around for longer. So here's a lemma which is not really new. It's also
Sorry,
comes from
but in your definition, you say complete and separated, I guess you mean. So complete for you means that the limits do not have to be unique, but the separated gives you the uniqueness of the limits. So that's just to make sure that I understand the word complete here. Every Cauchy sequence has a limit, but it doesn't have to be unique. That's what complete means here.
Yes.
Yeah. Okay.
Yeah. And separate really is translated algebraically in saying that the zero is intersection of cofinite ideals.
Right. Sure.
And completeness is translated to saying that this, together with separate, is translated to saying that this is actually an inverse limit of finite of Artinian commutative rings. So that's
but some definitions have separated inside the condition complete. That's what I'm saying. Some textbook there's never people never agree on this whether the complete should be separated or not. So I'm just want to make sure.
That's right. Yeah, thank you for saying that, and I completely agree. You're right. Many places consider separate as a subcondition complete, just as many commutative algebra books consider Noetherian as part of the word local. So it's a very good point. Yeah. So here's this lemma, which is, as I said, follows from work of Gabriel and some various literature. If you take a commutative ring with a cofinite topology, then you take its completion with respect to this cofinite topology. You can do that. So essentially, this is just the inverse limit of R mod I, where I is a cofinite ideal. You can see that this is the same. So let's look at this object E here. E is going to be the direct sum of the injective hulls of simple modules, but where you take simple modules that come from maximal ideals which are open. So I'm saying not maximal among open ideals, just a plain maximal ideal that is also part of the topology. So you take these maximal ideals, take the simple modules they produce, and take the injective hull. You take the direct sum of all these. Then the completion is actually the isomorphic to the endomorphism ring of this. So this is how all the complete rings, these pseudo-compact rings, appear. And there's correspondences between ideals, closed ideals of these things, and submodules of E. And as I said, these are profinite rings. So I'm kind of trying to give an introduction to these, and the classical examples. Classical well-known examples. This is the completion of K of X, of course, with respect to the topology of these, and that's actually cofinite topology. Or, of course, the ring of p-adic integers, which is the completion of Z with respect to the powers of the prime ideal P. And these are known to be actually the isomorphic to the endomorphism ring of the Prüfer group CP infinity. The endomorphism ring of that gives you just p-adic integers, of course. And for another example, it's the same example, but put all the primes together. The ring of Adels, well, actually there's, ring of Adels maybe has several versions, but if you just consider for this purposes, just the completion of Z with respect to all non-zero ideals. So this is like you consider on Z the full cofinite topology, or just consider all the primes and all the products. So the completion of Z is exactly a Z hat, which is just the product of all the ZPs for P finite. So these are examples of such profinite rings or pseudo-compact rings. And as I said before, they also appear naturally in representation theory when you want to study finite dimensional representations. But the last thing I want to say is this thing which I actually found quite surprising, that what happens if you look at a commutative pseudo-compact ring. So let's take a complete, so I'm looking at the diamond property in the complete case. That's what the theorem says. And I can, as I said, this ring is going to be the endomorphism of some minimal cogenerator. then R is Noetherian exactly when this is Artinian, so this is an equivalence. But probably the property that's interesting is exactly what Hans was saying before. This is Noetherian if and only if every ideal is closed, and is Noetherian if and only if this has diamond property. So the diamond property is in fact equivalent to Noetherian in the complete case. So this I found very, very unexpected somehow. And again says that this diamond property in many senses is not too far from Noetherian, and perhaps methods of this could be used in places in the non-commutative world, just also because of this. So anyway, I don't know, maybe I'm over. I apologize if that's the case. I'll just stop here, and thank you very much again for listening to me and for having me here.
Yeah, thank you very much, Mio. Very interesting, very interesting. Yes.
Thank you. Thank you.
Very nice. See, I always
Thank
tend,
you.
I guess, my mind setting is always on commutative Noetherian. So I realize that many times, I just assume Noetherian. And so this was very interesting to see in the more general setting.
Yes. Thank you. Yeah, it's very difficult somehow to even know what results work because of the world being Noetherian or not, like when we think about commutative algebra. So it's almost like going back to square one. But yeah. Thank you everybody for yeah, there was some comments in the chat. Yeah, for me it was as I said, I started just from conversations with some collaborators in Portugal, and then I realized that this is interesting in the non-commutative world. So I thought, okay, what's happening in the commutative world? That's the place to start to understand anything.
Yeah, thank you again.
Thank you.
Yeah, thanks. Thanks, Phil.
Thank you.
Thank you. Yeah.
So I think